When the wall switch is in the off position and the power is disconnected from the light outlet, the neutral and ground wires maintain their connection within the home's main electrical panel. This connection is fundamental to the electrical grounding system. Touching the ground wire to the neutral wire under these conditions effectively creates a complete circuit path. This path allows current to flow from the neutral through the point of contact and then through the ground wire. A ground fault circuit interrupter, or GFCI, is designed to monitor the balance of current flowing between the hot, or line, wire and the neutral wire. Under normal operating conditions, the current flowing in the hot wire should be equal to the current flowing in the neutral wire. If the GFCI detects an imbalance between these currents, even a small one, such as 5 mA, it interprets this as a ground fault. A ground fault indicates that current is leaking out of the intended circuit path and could potentially flow through a person, creating a shock hazard. When the ground wire is connected to the neutral wire, a portion of the current bypasses the neutral wire within the GFCI protected circuit. This creates the current imbalance that the GFCI is designed to detect. The GFCI then rapidly trips the circuit, interrupting the flow of electricity and preventing a potential electrical shock. The reason the neutral and ground are connected in the main panel is to provide a low impedance path back to the source in case of a ground fault. This low impedance path ensures that enough current flows to trip the circuit breaker or blow a fuse, quickly disconnecting the circuit and preventing a sustained fault condition. However, this connection also means that the ground wire is not truly at zero potential under all circumstances. Because the neutral wire carries current, there is a small voltage drop along its length. This means that the neutral wire at the main panel is at a slightly different potential than the neutral wire at the outlet. This difference in potential can be enough to cause a small current to flow when the ground wire is connected to the neutral wire, especially if the circuit is heavily loaded. This is why the GFCI trips even with the switch off and the light removed. The connection at the main panel is crucial for safety. It's also the reason why this scenario causes the GFCI to trip. Electrical codes, such as the National Electrical Code, or NEC, specify the requirements for grounding and bonding electrical systems. Grounding refers to connecting the electrical system to the earth, providing a path for fault current to flow back to the source. Bonding refers to connecting all metal parts of the electrical system together, creating a low impedance path for fault current. The NEC requires that the neutral and ground wires be connected only at the main service panel or the source of a separately derived system such as a generator or transformer. This single-point connection ensures that there is only one path for fault current to flow back to the source, preventing circulating currents and reducing the risk of electrical shock. In subpanels, which are electrical panels located downstream from the main service panel, the neutral and ground wires must be kept separate. This separation prevents the neutral current from flowing through the ground wire, which could create a shock hazard. The reason for this separation is to ensure that the ground wire is only used for fault current, not for carrying normal operating current. If the neutral and ground were connected at multiple points, the ground wire would become a parallel path for neutral current, and any fault current would be divided between the neutral and ground wires. This would reduce the amount of current flowing through the ground wire and could prevent the circuit breaker or fuse from tripping quickly enough to prevent a shock. The NEC also specifies the size of the grounding and bonding conductors. The size of these conductors must be adequate to carry the maximum fault current that could flow in the system. If the conductors are too small, they could overheat and melt, creating a fire hazard. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the size of the overcurrent protection device, such as a circuit breaker or fuse. In residential wiring, the ground wire is typically a bare copper wire or a green insulated wire. The neutral wire is typically a white or grey insulated wire. It is important to distinguish between these wires and to connect them properly to ensure the safety of the electrical system. When working with electrical wiring, it is essential to follow all safety precautions. Always turn off the power to the circuit before working on it. Use a voltage tester to verify that the power is off. Wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electrical wiring, hire a qualified electrician. Incorrect wiring can create a fire hazard or an electrical shock hazard. In addition to the NEC, many local jurisdictions have their own electrical codes. These codes may be more stringent than the NEC. It is important to be familiar with the local electrical codes before working on any electrical wiring. Electrical codes are constantly being updated to reflect new technologies and safety practices. It is important to stay up to date on the latest code requirements. There are many resources available to help you learn about electrical codes, including books, websites, and training courses. Understanding the principles of electrical grounding and bonding is essential for ensuring the safety of electrical systems. By following the NEC and other applicable codes, you can help prevent electrical shocks and fires. When a GFCI trips, it is important to identify the cause of the trip before resetting the GFCI. Repeatedly resetting a GFCI without addressing the underlying problem can create a dangerous situation. If you are unable to identify the cause of a GFCI trip, consult with a qualified electrician. There are several common causes of GFCI trips. One common cause is a ground fault in an appliance or electrical device. A ground fault can occur when the insulation on a wire breaks down, allowing current to leak to ground. Another common cause is moisture in an electrical outlet or junction box. Moisture can create a conductive path between the hot wire and the ground wire, causing a ground fault. Another cause is a loose connection in an electrical circuit. A loose connection can create a high resistance path, which can cause the current to flow through the ground wire. Another cause is a faulty GFCI. GFCIs can fail over time and may need to be replaced. To troubleshoot a GFCI trip, first try unplugging all appliances and electrical devices from the circuit protected by the GFCI. Then reset the GFCI. If the GFCI trips again, there is likely a ground fault in the wiring. If the GFCI does not trip, plug in the appliances and the electrical devices one at a time until the GFCI trips. This will help you identify the appliance or device that is causing the ground fault. Once you have identified the cause of the GFCI trip, you can take steps to correct the problem. If the problem is a ground fault in an appliance or electrical device, have the appliance or device repaired or replaced. If the problem is moisture in an electrical outlet or junction box, dry out the outlet or junction box and seal any cracks or openings that are allowing moisture to enter. If the problem is a loose connection, tighten the connection. If the problem is a faulty GFCI, replace the GFCI. In summary, touching the ground wire to the neutral wire with the power off and the light removed trips the GFCI because the neutral and ground are connected at the main panel. This creates a current imbalance that the GFCI detects, causing it to trip. Understanding this interaction and following electrical safety practices are crucial for preventing electrical shocks and fires. Furthermore, the NEC specifies various aspects of electrical installations to ensure safety. Firstly, the NEC mandates the proper sizing and installation of conductors. This ensures that wires can handle the anticipated current load without overheating, which could lead to fires. For example, NEC Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types. Secondly, the NEC requires overcurrent protection devices, such as circuit breakers and fuses, to be installed in electrical circuits. These devices are designed to interrupt the flow of current in the event of an overload or short circuit, preventing damage to equipment and reducing the risk of fire. Thirdly, the NEC specifies the requirements for grounding and bonding electrical systems. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electrical shock. Fourthly, the NEC addresses wiring methods, including the types of cables and conduits that are permitted for different applications. The NEC also specifies the requirements for installing these wiring methods, such as the spacing between supports and the protection of cables from physical damage. Fifthly, the NEC covers equipment installation, including the requirements for installing electrical panels, lighting fixtures, receptacles, and other electrical equipment. The NEC also specifies the clearances that must be maintained around electrical equipment to ensure safe access and ventilation. The NEC provides guidelines for special occupancies such as hazardous locations, healthcare facilities, and swimming pools. These occupancies have unique electrical requirements that must be followed to ensure safety. The NEC also addresses energy efficiency, encouraging the use of energy-efficient lighting, appliances, and other electrical equipment. The NEC is constantly being updated to reflect new technologies and safety practices. It is important for electricians and other electrical professionals to stay up to date on the latest code requirements. The NEC is a comprehensive set of rules and guidelines that govern the safe installation and maintenance of electrical systems. By following the NEC, electricians and other electrical professionals can help prevent electrical shocks, fires, and other hazards. When dealing with electrical systems, safety should always be the top priority. Always turn off the power to the circuit before working on it and use appropriate personal protective equipment. If you are not comfortable working with electrical wiring, hire a qualified electrician.